Hi, my name is Susanna. I'm going to be going over this combined stress loading problem for my ME304 summer class with Professor Lehman. Right, there's a few steps to this problem. I'm just going to start off by reading it off, and then I'm going to get into how we should take on this problem. Okay, so for starters, let me read the problem. Okay, for the beam shown loaded below, find the principal stresses. So this is what we need to focus on. Principal stresses, and the maximum shear stress, so at point A. Here we can see point A is right here, so this is our main focal point, and then we use the coordinate system shown, i.e. x-axis along the beam. So here we see the x-axis is in this direction, we have some forces in that direction, the y direction is going up. Here we have the 750 force in the y direction, and then in our z direction, it's going this way. We have a 500 Newton force applied there too. Okay. So how we would approach this problem, just how I would approach this problem. I would start off by plan 1, draw free body diagram. 2, find reactions, and I'll show you how to find that through a free body diagram right now. Reactions such as our x, our y, our z, as well as the moment in those directions. I will also show how to find moment, just to recap in case anyone needs to know that too. 3, we need to find our normal stress, our stress blocks itself, but I'm just gonna write stress blocks because this step itself has multiple steps in between. We use the reaction. Sometimes we can have up to 6 whole steps if we have a reaction in each one of these. So let's see. Oh, 1 second. All right, so we have our longitudinal stresses, and I believe it's called axial stress. Lateral stress, sorry, had to look that word up. Lateral stress. Our lateral in our longitudinal direction and our latitudinal direction. Alright, in our longitudinal direction for force, we have axial stress. So sigma x is equal to the applied force over the area. Right, and then we have moment torsion, moment which gives us torsion. This will actually give us, this will just give us our regular stress in the x direction, and then this would give us our shear stress in whatever plane we are looking for in that specific place. And then our lateral direction, our force will give us transverse shear, so this also gives us shear stress, and then our moment in the lateral direction will give us bending. And with bending, we also get normal stress. And then we find out if it's in the x or y direction, and then we use that to do our stress blocks, and I will get to that when we get there. So our first step, then the next step, I guess I'll do it here. 3, continued, just to continuation. 4, in this process, we are also going to be doing our stress blocks for each part, so we'll go through that when we get there. And then our 4th step would be combined stresses. Where we add all of the stresses together in each direction, do the sum, and then try to find our principal stresses. stresses. Sorry, my handwriting is so messy. Alright, so this is our plan. Gonna leave this up here. Okay, and I guess we can do our first step. So, step 1, free body diagram. Okay, I'm gonna use a pencil for this because I might have to erase a good amount. Okay, so our free body diagram taken from our A points, we're gonna cut around here, and we're gonna take the reaction from the X, Y, and Z plane as well as the moments in each direction. Okay, so when we cut it, we get this cut right there, here, do that block, draw out this block here. This is, I'm just gonna use purple to do it, just to see it better. That is our A. Here we have this 754s. Just gonna kind of draw it like messy because, you know, it doesn't have to be perfect. Here we go. It's just the diagram. As long as you get everything you need on this diagram, it should be okay. 500 newtons. These will get us 16 millimeters. Try to make sure you have all of your units. Your units accurate. If not, that will mess up your calculations and require you to start all over, and that is never fun. So here we go. This one is 440 millimeters, and this one here is 180 millimeters. Sorry, I write sideways. And then here we have 60 millimeters. And then 32 millimeters. And lastly, I think it's just this one left. This distance from A to this end on the y-axis, this is 30 millimeters. Just drawing on there. Okay, and now this is where we draw our reactions in the free body diagram. So using our system, we have X right here. So this is gonna be R of X. Our Y goes upward in the Y direction, our Y, and then our Z is going to be along this line, our Z. Right, I'm going to go over it with a pen so we can see that better. Especially the Z one. Alright, and then our moment's going to be about each of these axes. So, moment in the X, moment in the Y, moment in the Z direction. Okay, so now we have all of our forces, we have all of our dimensions, and we have our reactions drawn. Now we just have to find our reactions so that we can finish our step 2. So we finished step 1. We can cross this one off because we already did it. Okay, I'm gonna put this up here. Let me see if you guys can see. Right there. Alright. So now we have to to find the reactions, we need to use the R vector and the force vector to find the moment vectors as well. So just gonna do a little chart here to make it easy and organized to reference. Alright, so right here we have 1, 2, 3 loads, as we can see from our diagram. So I'm gonna do 750 Newton load, the 500 Newton load, and the 10 kilonewton loads. Remember, this is kilonewtons, not newtons. Make sure it's times 10 to the 3 or just 10,000, I guess. Right, and then right here we will have our R vector, our force vector, and our moment vector. I left some space on the bottom to do I, J, K. A recap of statics: I is in the X direction, J is in the Y direction, and K is in the Z direction. So when we get to that, same thing here. K, here, I, J, K. Right. We also know that moment is R cross product of the cross product of R and F. So we'll also go over how to do that, right? So starting off, we have R for the 750 in the X direction. It is 180 millimeters, right? And I'm just gonna per millimeters here to keep in mind of our direction and just our units. So this is gonna end up being in newtons per millimeter. I like to keep it in the regular units and just change it towards the end. I don't really like messing up with it until I absolutely need to. So I'm gonna leave this in millimeters for now. So 180. There's nothing in the J direction. It's just at this point, so it's gonna be 0. There's nothing in the K direction, so there you go. All right, and then we know that the force is 750. It's actually going down opposite of where the Y direction is, so it's going to be negative. So the Z direction, nothing is happening. The X direction, nothing is happening. In the Y direction, it's going to be negative 750, and in the Z direction, nothing's happening. Okay, so I'll just go over the first one so we can have a recap of how to do this. So this is going to be 180. 0, 0, cross product, 0, negative 750, 0. Alright, and then we make this into vector multiplication. This is I, J, K, 180, 0, 0, 0, negative 750, 0. Okay, then this will give us I, 0, 0, negative 750, 0. Minus J, sorry. So when we do the first part, it's I time cross this one minus this side. So we just put it here, and then the J will be 180, 0, 0, 0, so 180, 0, 0, 0, plus K, and it'll be the square, so 180, 0, 0, negative 750. There you go. And then doing this part, we get I 0 times 0 is 0 minus 0 times negative 750. I know the I is going to be 0, so I'm just going to 0 I for now. We don't calculate that. In the J direction, 180 minus 0 is 0. 0 minus 0 is 0, so J is 0. And then K is 180 times negative 750, right, minus 0. So then we get the moment is 0, 0, and then 180, negative 180 times 750. Moment is equal to 0, 0, and then this comes out to be negative 135, 0, 0, 0. So there we go. Right, and then we plug this in over here. 0, 0, negative 135, 0, 0. Sorry, I did not explain how to find a moment correctly, or that great, but it should just be a recap. I shouldn't have to go over it completely, but when you do 3x3s in this case, you just put the I and then do the 2x2 here, the J, and then you don't use these values, you do the outside. Same with the K, you wouldn't use this row, you would use this 2x2. And then you would do the same thing, cross multiply. I guess you can say if it was here A, B, C, D, you would do A, D minus B, C. So just you do that for each of them, and then always remember this is subtract, like minus J. Sometimes it's important. In this case, J is 0, so it doesn't really matter, but remember this negative is important. Okay, so I'm not going to go over it for the rest of them. There was just a recap how I found the moment, just to make this video shorter. Okay, so for 500, we know it's here. It is 180 plus 40 millimeters, so that is going to be 220. There you go. There's nothing, it's only in the X direction, so 0, 0. The same with this one, so I'm just going to do it while we're here. It's 2, 0, 0. And the I, and the, oh, so sorry, for force, It's not going in the x direction, it's actually going in the z direction, and it's going in the positive z direction, so it's going to be 500, sorry, 0, nothing in the y either, and in the z it is 500. Right, I'm not going to go over how I did this part, I'm just going to put what I got because I did calculate it ahead of time. There you go, you just follow the same thing, substitute these values here, substitute it like this, and then solve for it how I solve for it. Alright, and then for the 10 kilonewtons, sorry, we have our force here in newtons, so we need to keep in mind that it's in newtons, not kilonewtons, so don't pretend, put 10,000. Alright, so it's only in the x direction, so 10,000. Nothing in the z, nothing in the y. Alright, and we calculate this, we get nothing. So there's no moment in the x direction. Alright, and now that we have these calculated, we can find our moments, our reactions, our x, our y, our z, that's not m of x, m of y, and of z. Alright, so calculating this is going to be the sum of the moments. It's going to be the opposite of the sum of the moments. So, our r of x, our y, our z are computed from our force. So in the x direction we have 10,000. Our reaction is going to be negative 10,000 because it's going to be set to equilibrium, so it must equal 0. So 10,000 plus negative 10,000 will equal 0. And these ones are in newtons. These are going to be newtons per millimeter. Keep that in mind. Alright, and our y direction, it is 750. There's only one reaction, there's no need to calculate it. And our z direction, it's going to be negative 500. Alright, and then our moment, same thing, the thing in the x. And our y, it's going to be opposite sign of that, so 11,000. Here it's going to be 35. There you go, newtons times millimeter, and here it's just newtons. Okay, so now that we found our reactions, we can cross this step out. I feel like that was the most tedious step. I find the other steps a little bit more easier, but we can move on from there. Let me make sure I'm recording. Okay. Alright, so starting off, we're going to start off with our longitudinal reaction. So we find our longitudinal reaction by looking at our diagram. So here we have our longitudinal direction is actually our x-axis, is the one going through our system. So we can just write it down here that this is our longitudinal. And these are both axial, so you don't have to write it. As long as you know which one is your longitudinal, the other ones will be axial. Right. So, starting off, we start off with our axial one, so our x. We said that this one, in our longitudinal direction, will give us axial stress. So since this is force, we're gonna find axial stress. Here we go. And then finding our axial stress. Alright, so finding our axial stress, we're going to use our xy plane here. Take a little cut. Y, x. This is our system, and this is where we're going to cut it. Alright, and if we look at it from our diagram, oh, right there, where this is y and this is x, we can see that our A is going to be in this top corner, right there. Alright, and then finding our stress, so our stress in the x direction. We also have to know that it's P over A. Where's our P? Our P is given right here, the stress in the x direction, so it's negative 10,000. I'm sorry, this is x. Negative 10,000 in the x direction, so it's going to be opposite of where this x is pointing, so it's going to be this way. 10,000, and because these are pointed opposite of each other, it's actually going to be a tensile load, which means our P is actually going to be positive. I know it's confusing. Sometimes you don't focus on the numbers you're given, you're focused on the direction the diagram gives you. And that's how you calculate it. If you look at these directions and if you put that P is negative 10,000, you would get the wrong direction and you'll get the wrong answer. So focus on the direction rather than the numbers that you're given. Positive P over A. So we know that this is 10,000 newtons over, and then our area is actually going to be our area from our end view. So here you go. In our end view, we know that this is 32 millimeters, 60 millimeters. Right, so this is base times height. It's 10,000 newtons over 60 times 32. It's going to be millimeters squared. Alright, and this gives us our axial stress of 5.20833 newtons per millimeter squared. Alright, now I'm just going to convert this to newtons per meter squared to give our pH just for simplicity. 5.20833 newtons per squared times 1,000 millimeter, 1 meter, and then this is squared to cancel these out. Here we go. It's going to 5.20833 times 10 to the negative 3 squared meters squared, newtons per meter squared. Newtons per meter squared is 1 Pascal, so this is 5.20833. It's positive. Times 10 to the 6 pascals, which is 5.20833 megapascals. Alright, so we know that a Newton per millimeter squared will actually give us megapascals, so we don't actually need to compute that for the next one. So 1 Newton per millimeter squared is equal to 1 megapascal. Just for our next calculations, we don't have to recalculate that. Alright, so moving on to our next stress, Here you go, we have our latitudinal force. This will be, as we said before, lateral, we're going to have to use transverse shear. Transverse shear. Alright, same thing, x and y direction. Here it goes, block. RA is up here. Alright, and then our force in the y direction is 750, positive 750, so going up. Gonna go a little faster because I kind of already explained directions and all that. So this is 750 in the positive y direction. Alright, so transverse shear is equal to T is equal to, BQ over J. Yes. Alright. Sorry. Over IT, sorry. Right. Where V would be 750, our Q would be our Y bar times A. Our I would be, since the square would be 1 over 12 times base times height cubed, and then our T is thickness, so whatever thickness we have at that point. Alright, in this case, since it's in the corner, there is no transverse shear, so our T is 0. Oh, sorry, I forgot to do our stress box at this point, so I'm just going to go back. So our RX, axial stress. Actually, I'm going to do the stresses on a separate page. There you go. So for our x axial, right, we have these stress blocks. And I'll show you what they mean. So this is x, y direction, this is x, z direction, this is z, y direction. We do the blocks. Alright, and then our axial stress will give us, we already said 5.2 megapascals, and we know that it's in tension. We also know that it's in the positive x direction. So anything in the positive x direction, we can only use these two blocks. Positive will be this way. Alright, so then opposite would be that way. Here you go. There we go. It wouldn't make sense to have them both pointed this way. I feel like that would be 0. Right? And then we know that this will give us x is equal to 5.20833 megapascals. Alright, and then we know that our y transverse shear gives us these stress blocks. Remember, shear is 0 for this one, so there's nothing. We don't have to apply any stresses. Alright, and then moving on to our last reaction force, our z. Our z is equal to, we also have to find transverse shear. Alright, and because we used the x and z direction here, we're going to have to use the x and y direction in this one. It's just going to be the direction that you're not using. So in this case, since we use the y direction, this has to be x and z. For transverse shear, so in this case it would be jump block, it would be y and x. So the opposite one. So since we're using z, it'd be x and y. Alright, and then we found the force to be negative 500, so the opposite of the y direction would be up here, positive 500. It's still negative because it's the opposite direction, so only focus on the diagram. Even though it's going up, doesn't mean it's positive. Alright, and then in this direction we know that our A is right here because we're looking at it from the top. Sorry. Oh, sorry, this is actually Z. Let me see. What? And this was Y. Yeah. Sorry. I mixed up the directions. So I meant the opposite. You're supposed to use the direction you're going in and the x direction for transverse shear. I think I was talking about moment. Sorry, I'll get to that. Didn't mean to confuse you. So 500. So T of A, sorry, these are all of A. It's important to note them for when we have multiple points we need to find for. In this case, we only need one, so we're just going to stick to that. T of A, we said VQ over IT. Okay, we know that our V is negative 500. We need to find our Q. Our I, we'll find this using our end view, and then our T, we'll find it using our end view as well. Okay, so we have our end view. We'll use another page. Right, end view. Alright, so we're going to be looking at this cross-sectional area. This is our end view. Here we go. Alright, and if we look at it from this direction, our eye actually lands on the top. So this is where our A is going to be. Fill that in. A. Right, we know that the height is 32 and the base is 60 millimeters. So our I is actually going to be of this top, no, our I is going to be of the whole square. So it's base 60 times the height cubed, so 32 cubed over 12. Because the eye of a square is 112 base times height cubed. Alright, and then looking for our Q is equal to y bar A. Our y bar is the center of the top square from the center, from the neutral axis. And because this is where we already know by symmetry that this is going to be our neutral axis. This is center. Alright, so it's going to be, the neutral axis is half, and then half of the half is going to be 8. So I'll just write it better. So 32 over 2 will give us the half, and then this divided by 2 will give us our y bar. And then our A is the area of this square, like I said, right? And that is going to be 16 times 60, right? This gives us 8 times 60, which is equal to 7,600 is our Q. All right, and going back to our transverse shear equation, sorry, there's so many pages. T of A is equal to BQ over I of T. Oh, I also forgot to mention our T as well is going to be 60 because our thickness is going across the horizontal plane, so it's going to be, T is this distance crossing it. T is 60. Alright, so this is, like we said, negative 500, 7,600, I 1 over 12, base 60, height is 32 cubed, and then RT is, we said 60. Okay, calculating this transverse shear, and at point A we have 0.390625 in negative newtons per millimeter squared. We already did calculations. We found that, where is it? 1 Newton per millimeter squared is equal to 1 megapascal. So we know that this is also equal to megapascal. We don't need to redo that calculation. It's a 1-to-1 ratio. All right, and now doing the stress block for that. So RC transverse shear gives us this stress block. Let's just draw these stress blocks real quick. They're all the same, X and Y throughout this, X and Z down here, and then Y and Z on this in this direction. Right, so we do have stress in the, we have negative shear stress. So it's actually not going to be our normal shear stress where we have a block and our stress is going to be like this. Not necessarily in every case. It's actually going to be negative of the direction of our planes. So we also know that this is only applied to certain planes. In this case, it's going to be only in the X and Z direction because we're only using the X and we're only finding X and Z transverse shear. So it's only going to be here, and like I said, it is going to be negative 0.39. So negative X is, negative X is this way, negative Z is this way, and then our opposite reaction, so this way, right? Right, and how I like to determine if it's positive or negative, I do dots where the arrows are, and I connect the dots, and if they have a positive slope, then it's positive, and if it has a negative slope, where in this case it would be negative here, then it's negative. So we actually have positive transverse shear in the X and Y planes. 0.390625 megapascals. Alright, and then we can move on to bending. Put this off to the side. Sorry, get rid of some of these pages. Get rid of this one. Alright. Right, We have no moment in the x direction. This would be our latitudinal moment, which would give us torsion. We can skip that, we don't really need it, but just so you know, torsion is equal to the torque times rho is the outermost fiber times over J. We're not going to need this. Okay, so we have M in the y direction, which gives us bending. Okay, so this is where I meant that when we have a moment in the y direction, we're going to look on the x and z planes. So it's as if y was sticking out looking towards us, and then using like the hand rule. So since our y is here, we'd have to look at the other two planes facing down towards it. I forgot what it was called. Yeah, but you can use your hand rule. Alright, we have, so we're gonna use the x and z. Oh, no, I did. There are x and z planes. Yeah. And then looking at the top, we already did another figure, like another diagram like this. This is where A is. Alright, and then our moment in our y direction is actually positive 11,000. So when a moment is positive, it's going counterclockwise. It's going counterclockwise, so it's actually going to be this way. Alright. And our moment at A is actually 0. Gives us a 0 stress. Stress of A at 0. And this is because our moment, our stress is equal to moment times y, the outermost fiber, over I. This is because y is 0. There is no distance from the center to the point, so it's automatically 0. Doesn't matter how we calculate it, we're gonna get 0. So no stress blocks. Gonna just do moment of the y. There's nothing, so 0. Right, and lastly, moment in the z direction, which also, we will also use bending. Great example, like I said, we're gonna use the plane that we're not trying to look for. So if we're trying to find moment in the z direction, we're gonna use the y and x plane. Right, and then we know that our A is here, based on previous diagrams. X, Y, right, and then our moment in the z direction we found to be 135,000 in the positive. So in this case, it is going to be clockwise. You don't have to write this as 11,000. Here's 1,000 newtons millimeters squared. Alright, and like we said, shear stress is equal to moment times y over I. Alright, we already know that our I is equal to 112. Base, which is 60, times height, 32 cubed. Right, our y is our distance to the outermost fiber. If we look, if we look off our end view, we already know that it's going to be 16 millimeters. So we're the 16 millimeters, distance to the outermost fiber from the center, and we know that our moment is 135,000. All right. Sorry, this is stress. I don't know why I said shear. Yeah. Okay. Alright, and then looking at this moment picture, the moment is actually pulling on A rather than pushing towards A, so it's going to be in tension. So regardless of our whatever sign we get, this is going to be positive. So we'll just calculate it here. Here we go. Here is millimeters squared. 16 millimeters over 112. 60 times 32 cubed millimeters. So 4. Alright, this actually gives us a positive number regardless. It's at 13.183 megapascals. It's newtons per millimeters squared, which gives us megapascals. It's the same value, just different units. Megapascals. Right, going to the stress block. This is our final stress block in our z direction. Here we go. Alright. Sounds good. Alright, so this is only in the x direction, so, and it is positive, so we do what we did for our first one. Sigma x is equal to 13.183, and I only do this on one page because when we combine them it's just so much easier to look straight down rather than flip through pages, and I wanted it to be easier. Okay, so since we are actually done with our stress blocks, I'm gonna cross out the ones that have nothing, so we can ignore this one and we can ignore this one, so we only have 3 sets of stress blocks to look at and combine. So we finished step 3, now we're on to step 4, combined stresses. And we only need to look and refer to this page now. Alright, grab another page. Okay. Combined stress blocks. Okay. So I'm making an overall one here. Oh, that was too close. This one anyways. I've done too many of these. Alright. X, Y, X. Okay. Alright, so starting off, we know that we have a positive 5.2. We have a positive 5.20833, and then in the x and both y direction, but I'm only going to focus on the x for now. And then on the bottom we have a positive 13.183, so we're going to add that positive 13.183. They're both positive because they're both in tensile stress, not compressive. If one was compressive, we'd subtract them. There was compressive means negative and tension means positive, so 183. This gives us 18.3913 positive, 18.39133 megapascals. Right, in the xy plane, and then going to the xz plane, we have the same thing actually. We have 5.2 and we have 13.133. Sorry, I don't know if this is confusing anyone. Alright. So it's going to be the same thing, 18.39. I'll just sum it up like that. Alright, but we also have this transverse shear in the xz plane. And it is positive. Transverse shear, gonna write it up here. It is 0.390625 megapascals. And if we look in the YZ plane, there's nothing, so we can ignore that. And then we need to decide here what is our critical plane, which values are we going to use. So we look at the stress block with the most stresses added to it. So in this case, this will be our critical plane. Critical plane, and from here we know that our sigma x is equal to 18.39. What did I say? 133 megapascals, and our shear in the xz plane, this is important, xz plane is equal to 0.390625. Okay, and we have no force in the z direction, that's 0. And we have found our normal and shear stresses, so we can say that we finished the step and we're off to the final step. We're off to the final step, the easiest step in my opinion, principal stresses. Principal stresses. Right. And this one is fairly easy enough to do. It is pretty simple. We follow this equation, so sigma 1, sigma 2 is equal to sigma x, sigma z in this case. If it's a two-directional plane, it'd be y, but since in this case we're actually using the z direction on the z plane, it's going to be sigma z. So over 2 plus minus the square root is sigma x minus sigma y, 2 squared plus tau x z, z squared. Okay, substituting these values in here, 18.3133 plus 0, I'm getting, well, 0 over 2 plus and minus, sorry, 18.39 minus 0 squared plus 0.390625 squared. Again, these are in megapascals. Since their stress is going to be the same units, so I'm not going to write it. This gives us 9.195665 plus and minus 9.20395. Alright, this is higher than this one. When we add them together, we get our sigma 1 for maximum stress, which is 18.3996 megapascals, and we get sigma 2 is equal to the difference of these two, which is negative 8.2293 times 10 to the negative third megapascals. This, it's a really small number, it's like 0.01. I'll just leave it like that, that's what I got. And then our tau max. Our tau max is actually just this number. I can write the equation for it. It's just tau max is equal to the square root of sigma x minus sigma y over 2 squared plus tau xz squared. So there's no need to do that. It's just this value here. So is 9.20395 megapascals. And I believe that is all. Oh, sorry, my fortune. Just sign this off. And okay. And I believe that is all.